All right. Welcome back, everyone. Hope we had a good, productive weekend. So, Math 162, Week 4, Lecture 1. This is our seventh meeting together. Might seem like it's been more, but it's the seventh. Just reminding us of some due dates that we've seen before. 5.5 and 5.6 are both due on the 17th. Everything else was due previously because it had been assigned more than a week ago. And we started 5.7. We got what, like 30 minutes into 5.7, if even that far, maybe 20 minutes. Last class, we will finish 5.7 today. So it is due in a week after that. Remember, all due dates are 11:59 p.m. for the time of said due date. And when we start 5.7 today, I'm actually going to cover the very last 5 minutes over again. You're going to see it exactly the same as before, just to kind of get us into the groove of things today. I feel like that's going to be the best way to reintroduce the idea of the inverse, just to go through that inverse cosine graph, how we restricted the graph of the cosine to actually get an invertible graph so that it passed the horizontal line test, all that stuff. And since we're finishing 5.7 today, and we will finish 5.8 next class, I can guarantee that. That means that we'll have our first test a week after that. Remember, I said that we always do our tests a week after finishing the material on them. The only exception, it would be like the final exam, because, well, I mean, final exams are the day after the class after finishing everything for the course. So there's no way to avoid that. So as a reminder, the way we do tests in here, something we talked about many days ago, I will give you 2 full days to take a test. Now, we will still hold regular class when these test days fall on a regular class day, which I generally make them fall on a class day as well, and then a day before or after. So 48 full hours to take your test. The test will be 2 hours. This first test will be 25 questions. They're not all going to be the same number of questions. Test 2 and 3 will have significantly longer problems here and there, so the number of questions will be reduced. And you will find the test in the quiz and test section of my math lab. I think that makes sense. So it's due 11:59 p.m. the 25th, which is a Friday. So if you don't want to be taking your test on a Friday night, then I'd advise you to take it before then. I know a lot of people like to wait till, the last second to take things, and if you do, that's your decision. That's why I give you the time, but I do suggest taking this sooner than later, especially because you just never know what kind of technological issues my math lab might have, and they love to do these things late on Fridays sometimes, or on Saturdays or Sundays and whatnot. So this is a math class and a math test, and math generally requires showing your work. We show a lot of work in class. So the test is going to be in my math lab, and it's done just like your homework. So if you get something right, it gives you credit. If you get it wrong, it gives you no credit. But I understand that the problem might have 4 or 5 steps, and you did some of those steps right and just got the wrong answer. So while the question may be worth 4 points, maybe you deserve 1 or 2 or 3 of those points back based on your work. So this is why I say you must submit your work in Canvas. Now, first of all, well, actually, 2 things. First, if you can hear my dog sawing logs behind me, I'm sorry. One of the many distractions from home. Second of all, if you do not send any work, I have the right to refuse to accept your grade, because I don't know if you actually did this or if some, form of plagiarism has gone on. So you have to show some work, you have to send some work. No work means I reserve the right to give you a 0 a test, something I absolutely do not want to do. You can handwrite your work. If you are capable of typing your work, you can do it that way, which is not what I expect anyone to be doing for a test, especially since you have to submit it within 15 minutes of finishing. Again, just to make sure that there is no funny business. It would be very hard to have a lot of funny business go on in that 15 minutes. So you can take a picture of your work, and then upload that file into Canvas. You can't see where that's available currently when you log into Canvas, but it will be available those 2 days of testing, and it should be very obvious since we don't have a very heavily loaded Canvas course. It'll just say submit test 1 work here. You only get 1 submission, so make sure you submit the right file. Please double check that. Please make sure you write your name on each page of the files you're submitting. Please make sure your work is numbered. If your work is not numbered, again, I refuse the right to not give you credit. Now, you must email me if you want partial credit on question 2 and question 5 and question 13. You need to send me an email after you finish, after you submit your work, and say, hey, Mr. Beckner, can you check out questions 2, 9, and 15? I think I've got some good work. Maybe you can find some partial credit for me. So you send me that email, and then I'll look over your work, and then I'll respond to you and let you know, yeah, I was able to find some points, and maybe I even found a couple points you didn't know about. But if you don't email me, then I'm not going to look for partial credit. So it's not going to take a lot of time for you to do. It's just very, very, very complicated the way this stuff is set up to have to go through individually, and it would just take 5 more hours to look over everyone's work without knowing ahead of time what to look at. Much different than just having a stack of papers in front of you, unfortunately. But I am trying to give everybody the benefits here and still get you your partial credit. You know, I figure if I can scratch your back a little, you can scratch mine by sending that email to make it easier for everybody. I also promised that I would give you review assignments in my math lab. They are located in the homework, and the review for this test, I believe I made it available almost a week ago. You should see it directly under the 5.8 homework. Now, that review is not going to be graded. Whether you do it or not, it will not affect your grade at all. There's no bonus points, there's no extra credit involved with it. It's just there to help you study. The review is very comparable or comparable, depending on your phrasing, to the test. So the review will help you narrow down what you should be studying on. So if you, maybe on the review, I don't have the graph of some super crazy tangent function, then you know that you wouldn't see that on the test. So again, that's going to help you know what to expect. The problems on the test will be a very familiar feel to the problems on the review. I advise you to do this. And I will say historically, the people that make A's and B's on the test are the ones that do the review, and the ones that make F's and D's on the test, well, I think you can imagine whether they do the review or not, as well as the homework leading up to the review. Time invested is generally rewarded, and we want good rewards. We want good grades. We want y'all to do as best as you can. So invest the time, do the review, do the homeworks, and everything should feel familiar. This is a no calculator test, which I failed to write here. It's something I mentioned week 1, that test 1 and test 2 will be strictly no calculators, but test 3 and test 4, you will be allowed them. So do not use a calculator for this test. And there will be times that I can tell if you used a calculator. If the answer is supposed to be square root of 2, but you answered 1.4, blah, 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 I'm going to know you used a calculator. And the second I see that, I'm going to take your entire grade back. And again, these are things I don't want to do. So please, please, please make sure you have been following the way we're doing things in class. I'm setting us up for success as long as you're watching the lectures, as long as you're taking good notes, as long as you see how we're typically approaching these problems. Per usual, if you have any questions past this, you can talk to me in class or email me after. But with that being said, let's go ahead and pick back up where we left off, as well as a quick little 5-minute review of how we got the graph of the inverse cosine. And if you want to see the inverse sine, that's part of the last lecture near the end as well. But again, I just thought this would be a good reintroduction.
So now let's do the cosine. So y equals cosine of x must be restricted domain of d equals, and some brackets, some space, close them. And this is going to turn out to be 0 to pi. Of course, it's not the same as sine. Why would it be, right? They always have these subtle differences, and you're not going to figure out and remember these subtle differences without practicing this stuff over and over, without writing notes, without taking notes, reading them over and over, going back to them, highlighting stuff, whatever. So cosine must be restricted to a domain of 0 to pi. Now, I explained why sine had to be restricted, so of course I'm going to do the same for this. So I'm also going to say due to this, which we'll say see below. So we're going to prove that we need to restrict the cosine graph to 0 to pi. So for y equals cosine of x, which originally, when you go forever left and right, heights of 1 and -1. We start at 1, and then we're going to go down and then back up and then back down, back up, forever and ever. And the same thing if we were going left, and they'd be a little prettier than what I have, but you get the idea. Clearly, this fails horizontal line test miserably, the same as the sine did without restrictions. So we got to cut this thing down. And the is, well, let's just go from 0 to 2 pi. So if you go from 0 to 2 pi, we know it starts at a height of 1, goes down, and then back up to a height of 1, eventually, like that. But clearly, fails, fails. That wasn't a horizontal line, but it fails. It's a little slanted. So 0 to 2 pi is too much. So a lot of times we'll just cut it in half. And then if we think we need to go to the negatives, we will. So instead of going from 0 to 2 pi, what if you chopped off everything over here? Would that be good enough? Well, I don't see anything that looks like it would fail the horizontal line test, so let's try that. Let's just go from 0 to pi. All right, so that's now going to be a pi over here. You can put pi over 2 up here if you like. So cosine starts at a height of 1 here. And by pi over 2, it's going to be here. By pi, it's down at -1. But it's not a straight line. It bends. It waves. That's not the best wave I've ever drawn, is it? A little better than that. There we go. There we go. Much better. This appears to pass the horizontal line test. Passes, passes, passes. So we're good. Now, this is good, so 0 to pi works, but you might, it's always worth trying going to left a little. So pi is as far right as we can go, because if I went just a little further right, it starts bending back up, and that's where we start failing the horizontal line test. So you might think, all right, well, last time we were able to go left some. Once we chopped this down to pi over 2, we said, well, what if we can go left? And we were able to. But if we start going left from here, we're doing that, and again, we'd be failing the horizontal line test. So this is actually as much as you can restrict it and remain invertible. How are we on time? 30 minutes. So, same idea. Because the cosine is bound with a range of -1 to 1, that means the inverse cosine would have a domain of -1 to 1. And we've already established that since the domain of cosine is from 0 to pi, then it's the range of the inverse function would be that. So y equals, oops, holding my pen upside down, that doesn't help. Y equals cosine inverse of x has a range r equals 0 to pi. And again, that is because the domain of cosine is 0 to pi. And the inverse function has a domain of what the regular function had for range, which is literally the same as the sine, -1 to 1. So the domains of the inverse functions are these values because the regular graphs were stuck between heights of 1 and -1 when we didn't throw amplitude numbers in there. If I threw a 2 or 3 anywhere in here, that would change things in here. All right, something that I'm not really going to I don't want to say this, to really use moving forward. But here was the graph of sine to make it invertible. Here was the graph of cosine to make it invertible. Let's invert those graphs. So here we're going to do the graphs of the inverse functions, inverse sine and inverse cosine only. So all we do is, remember, we swap coordinates. That's all we're doing. So this point right here, which was -pi over 2, -1, would now be -1, -pi over 2. This point right here that would have been pi over 2 comma 1 is now going to be 1 comma pi over 2. That's the idea. This point here was the origin, so it's going to be the origin when you invert it. So again, taking that graph, can I do this? Yeah, it's going to be weird. What happens if I copy, paste? Oh no, that looks awful. We're just going to leave it there. Okay, I'm going to pull back some. All right, so first we're going to do is the y equals inverse sine of x. Again, it's just taking this graph right here and swapping all x and y coordinates. So the values going from negative pi over 2 to pi over 2 on the x-axis will now be on the y-axis. I'm going to scroll back just a little more. So now we'll have negative pi over 2 on the y and positive pi over 2 on the y. And then those heights of 1 and negative 1 that were on the x-axis, I'm sorry, that were on the y-axis originally, will now be on the x-axis. Then we just plot the points. So this was negative pi over 2 comma negative 1. So now it's negative 1 comma negative pi over 2. Then we had the point at the origin, which is pretty clear to see. And then pi over 2 comma 1 is now 1 comma pi over 2. Now, I'm not going to go in and do all the middle details because this is not something we're going to focus on throughout the rest of the course. But when you bend this way for the regular function, what that means is you're going to bend this way for the inverse function. It's just the way things work. So it actually kind of looks like a cubic here. So remember, the domain is the x values. The range is the y value. So it depends on, are you talking about the regular function or the inverse function? But when I say the word domain, we're talking about x values. When I say the word range, we're talking about y values. But just understand that when you talk about the domain and the range of the regular function, they flip-flop in the inverse function. So that's our inverse sine graph. Now, here's the thing. This does not extend. This is the whole thing. This is the entire graph. It's not like sine and cosine where those waves keep going on and on and on forever and ever. Because we had to restrict the sine graph to be something so small in order for it to be invertible, that means this has to be a relatively small graph as well. If you restrict the regular function severely, then the inverse trig function is not going to take up a lot of space either. Now, what's interesting is negative pi over 2 to pi over 2, this is between negative 90 and positive 90 degrees. So we can almost stay inside of one quadrant, but really that's in quadrants 1 and 4. So this is in quadrant 1 and 4. When you're thinking about your unit circle. And that idea is going to be extremely important because what we're about to do for the inverse cosine, you can probably guess, it ain't the same. So this time we're going to take the cosine graph, which had x values going between 0 and pi, so that's now our y values. Our y values are going to be going between 0 and pi. So something like this, x, y. So let's have pi up here, maybe pi over 2 here. Split it a little more evenly though. There we go. And then 0. So again, those x values become the y values, and the y values become the x values of negative 1 and 1. All right, so we had the point at 0 comma positive 1, so 0 comma 1 is over here. Then we had the point, and 1 comma 0 now, that is to say, 0 comma 1 becomes 1 comma 0. This was pi over 2 comma 0. You flip the order, so it's now 0 comma pi over 2, which is here. This was pi negative 1, so now it's negative 1 pi. And again, because of the bending this way, the inverse function would bend in a different way. So it ends up looking like this at the end of the day. And again, it does not extend. Here's what would happen if it extended. On the sine wave, basically, it's just instead of drawing your waves like this, when you invert the function, your waves get drawn like this. So when you invert a wave, that's what happens. But it's not a function, which is why you had to cut so much of it off. So if you kept going, that inverse sine wave ends up looking like, without getting wider, poor artistic ability on a blind tablet. And then it would do the same thing below. It would keep waving around. We can't do that because then it wouldn't be a function. The same thing happens with this cosine wave. It would come back down to the 1 and then back up to the, or back to the left of the -1, right to the +1. It would keep doing that same idea, but again, fails being a function miserably, and we only deal with functions in trig. So this, you're going from 0 to pi, which means we're in quadrant, let's go back to blue, 1 and 2 in your unit circle. Again, the fact that sine inverse goes with pairs with quadrant 1 and 4, and cosine inverse pairs with quadrant 1 and 2, that is going to be a major, major, major issue moving forward. This is an issue that a lot of people mess up the first dozen times they do it, and then the second dozen they start getting used to it and getting them right. When is this going to be an issue? When negatives are thrown around. It's always the negatives that mess us up, right? Oh, sine of pi over 3, I know how to do that. Just use that little right triangle, the 1, 2 square root of 3 triangle. What if I ask for sine of, you know, some other value like 5 pi over 3 when we're another quadrant? And it's basically the same thing, except it might be negative. It's that same idea here, except it's not the whole. There's 2 answers. It's only 1, because these aren't going to be valid in all 4 quadrants, only 2 of them. So while in the past, we might have been saying, all right, find all x where sine x equals square root of 3 over 2, that's going to be different than how I'm going to ask it today. And with the very first example, I'll show you the difference there. So am I going to ask you for these graphs repeated throughout this course? No, that's not what I'm going to ask you about. I'm going to be giving you examples like find sine inverse of square root of 3 over 2, or find cosine inverse of square root of 2 over 2, or find sine inverse of 0, or cosine inverse of 0, or sine inverse of 1, anything like that. So I'm basically giving you the ratio of opposite, adjacent, and hypotenuse inside of that inverse trig function, and your answer is supposed to be an angle. We've answered questions like that, but it wasn't using the inverse notation, which is why it was different. When we use this notation, we're restricting ourselves to half a circle by nature. All right, so enough blah, 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 right? Let's get down to it. Let's zoom back in. Example 1, evaluate that A, let's go back to black. We're gonna have the inverse sine of the square root of 2 over 2. So this is the question. This by itself is the question. This right here are your opposites, adjacents, and hypotenuses, hypotenuse, whatever would be respective of this trig function. So sine is always opposite over hypotenuse. So I'm saying that we could form a little right triangle where this would be the opposite and this would be the hypotenuse. Except it's going to be a little funky and it would be harder to find the angle because of this weirdness. So that's where I say, oh, it's actually a really good idea if you remember that square root of 2 over 2 is 1 over square root of 2. But here's what we're doing. So blue, this is not the problem anymore. This is what we're doing. We're trying to find an angle. Our goal is to find an angle such that the sine of that angle is equal to square root of 2 over 2. But restricted because the problem had an inverse trig function. So in like the second or third section of this course, what I have just circled in blue, I gave you that as a problem. I said I would say find theta such that blah blah blah, and I would also say that theta was between 0 and 2 pi, no or equals there, and you would get two answers. Again, if just this blue circle thing was the problem, there would have been two answers because we could have talked about the full circle, but it's not the case. Because we're talking about an inverse trig function, these inverse trig functions have restrictions. Specifically, sine, you're stuck in quadrants 1 and 4. Cosine, you're stuck in quadrants 1 and 2. There's an even bigger issue here. It's not that you're just stuck between quadrant 1 and 4, but if you wanted to answer, say, 330 degrees, that's wrong. Even if technically speaking, 330 degrees is coterminal to the correct answer. The correct answer would be negative 30 degrees because this thing does not go between 0 to 2 pi, and 330 would be up there near 2 pi. It goes from negative 90 to positive 90. So you would have to turn that 330 degrees into negative 30 by doing coterminal angles. You've got to understand how that works. Which the cool thing with negative angles and sines is you just make it negative of the reference angle. It's pretty easy, in fact, as we'll see. Okay, so we're trying to find an angle such that the sine of that angle is square root of 2 over 2. This is the same as trying to find the sine of an angle that's 1 over square root of 2. So that tells us to use the 1, 1 square root of 2 triangle, which is right here, 1, 1 square root of 2. Sine would be 1 over square root of 2, opposite over hypotenuse. So the angle is 45 degrees, but we're going to keep everything in radians for this. It's another issue. With inverse trig functions, these need to be in radians. You are not supposed to use degrees for inverse trig functions. I do believe my math lab will mark that wrong. So theta would be pi over 4. And because this was positive, that's the answer. If you don't believe this, the sine of pi over 4 is square root of 2 over 2. So the inverse sine of square root of 2 over 2 is equal to pi over 4. That's what we're saying. We are saying that the inverse sine of square root of 2 over 2 is equal to pi over 4. We're finding angles when the question is an inverse trig function. We're finding ratios of opposites, adjacents, and hypotenuses when the question is a sine or cosine problem. So in red, so like in, I think this was 5.2, 5.3, the question would have just been this. It would have been find theta, so the sine of theta is equal to square root of 2 over 2. Sorry, find all theta. Find all theta, where 0 is less than or equal to theta is less than 2 pi. So full circle, well, we'd say, oh, well, we need a reference triangle for this. So a reference triangle, and again, that's 1 over square root of 2. So you put your 1 here, you put your square root of 2 here. This is your reference triangle. That makes this also a 1, and that makes the theta prime 45 degrees. But then you say sine is positive in quadrants 1 and 2. Because sine is the y value, you go up in quadrant 1 and 2. So the first solution is the reference angle of 45 degrees, which is pi over 4. But theta 2 should be in quadrant 2. So you put your reference angle of pi over 4 there. That's in quadrant 3, excuse me. 2. So this right here is your pi over 4. This right here would be your second actual angle. And when you do pi minus pi over 4, it turns out that theta 2 is 3 pi over 4. So pi over 4 and 3 pi over 4 were the solutions. But with this inverse trig, because of the restrictions, it's only one solution. inverse sine is not valid in quadrant 2. So in the actual problem, because we worded it this way, we can't involve quadrant 2. That's why we have to toss it out in this problem we just did. That is a big distinction. That is a distinction that people mess up. I'll see students in the red ink, if I gave them the red ink problem on a test, which I certainly can, they only give me one of the answers. And then I'll give the inverse trig problem and they give me 2 answers. You've got to keep things organized. You've got to know when to restrict, when not to restrict, when to use the full circle, when not to. And when you have restrictions, what are the restrictions? Where are you stuck to? All right. B, black, not blue. We're going to do inverse sine of -1. Okay, so the idea here is the problem that you're really doing is you're finding, again, the black ink is the whole problem. But then what you're thinking about is finding an angle such that, or so, the sine of that angle is equal to -1. But restricted to what? Quadrants 1 and 4. So again, now in the blue ink, this is more like something we had in 5.2, 5.3, but I'm not going to consider all 4 quadrants. I'm a lot less likely to get 2 answers. I'm much more likely to only get 1 answer. In fact, with inverse trig functions, it's always just 1 answer. All right, so sine being 1 or -1 only happens at the quadrantals, so we need to go to our unit circle. So we go to our unit circle, and we're trying to say, where's the sine, which is the y-coordinate, -1? Well, here's a -1, but it's the x-coordinate. Here's the -1 is the y-coordinate. So the answer in, that was weird. The answer in degrees is 270. In radians, that would be 3 pi over 2. So 270 degrees is the same as 3 pi over 2. And that does put us in between quadrants 1 and 4, so we're okay. So here's what somebody would do. They'll say, okay, so it's unit circle, it's quadrantal, it's at 270 degrees, which is 3 pi over 2. But if you put, and while those are arguably correct based on the periodicity of trig functions, if you put this in my math lab, if that was your answer, guess what it does? It marks it wrong. And it is wrong. It is coterminal to the actual answer, but because we use this inverse trig notation, the restrictions are very specific. Not only are we restricted to quadrants 1 and 4, the way we label values in quadrant 4 is specific in that we don't go from 3 pi over 2 up to 2 pi. We have to be using things between 0 and -pi over 2. Those are the values we would be saying. So 3 pi over 2 is the same thing as -pi over 2, and this is how you have to answer it for an inverse trig function, because 3 pi over 2 is outside of the range. -pi over 2, the coterminal version of that, just rotating clockwise instead of counterclockwise, is in the appropriate range. So that's the answer. That's the only way to answer it. So theta is -pi over 2. And I know it seems ridiculous that, well, 3 pi over 2 is the same answer. It's coterminal, and we've never had a problem with this before. And you are right that we hadn't had that problem before. But in life, very often, we have to restrict ourselves to a very small set of rules, parameters, values, whatever. And there's a lot of things we do with inverse trig functions, so this is important. In fact, your calculator is very likely to mess up inverse trig functions. About half the time, if you're not paying attention to your quadrants, it'll say, oh, it's this thing, because it won't worry about the restrictions and everything, and then it's actually wrong because it might have something to do with an issue like this, or maybe you put an angle that you think is in quadrant 2 and really it's supposed to be in 4, or vice versa. All right, let's do another one. We're going to do all bunch of these, clearly not all of them today, since we only have about 8 minutes left. All right, inverse sine of the square root of 3 over 2. Now again, we did problems just like this in a simpler way before, back in like the second and third section of this chapter. I would have said, though, find all theta such that sine of theta equals square root of 3 over 2, and the angles between 0 and 2 pi. And I even could have done restrictions there to kind of, get that idea going. I did that once or twice. So when you see this question, this is what you're thinking about. You're trying to find an angle such that or so that the sine of that angle is equal to square root of 3 over 2, but restricted to, and instead of saying quadrant 1 and 4, I'm going to be even more specific now, negative pi over 2 to pi over 2. That's still saying quadrant 1 and 4, but I'm being very specific with the language of how I have to write any angles from quadrant 4. I can't call them 5 pi over 3. I'd have to call it negative pi over 3. I can't call it 11 pi over 6. I'd have to call it negative pi over 6. Well, sine of theta equals square root of, sine of theta equals square root of 3 over 2. Well, that's our 30, 60, 90 triangle with opposite of square root of 3 and a hypotenuse of 2. So let's go over to our unit circle. Not unit circle, excuse me, the special triangles. 30, 60, 90, 1, 2, square root of 3. So we're just trying to figure out, is it the 30 or the 60 degrees? Well, we're doing sine, so the opposite's supposed to be the square root of 3, so that should be the opposite. This should be the hypotenuse, which says that our angle is the 60-degree angle, but we're going to use the radian version for inverse trig functions. Again, I believe my math lab should be marking those wrong if you put it in degrees. So our angle is the 60 degrees, which is pi over 3. Now, since this is positive, this should be positive. If that had been negative, spoilers, this would have been negative. I will not be surprised if Word crashes. It keeps giving me that blank, like, refresh thing. And I know if I hit save, it will, so I'm not going to hit save. So the angle is pi over 3. That's inside the appropriate window. And that's it. And again, that was based on the right triangles. D. Do we have time for one more? Yes, we do. And before I do D, I wanted to make that memo. I just said that, but I want to type it out too. So special note, if the inside of inverse sine negative, that just means the angle is negative. It's just the reference angle, but negative, because that's how going from quadrant 1 to quadrant 4 works. You're just spinning in the opposite direction. So I will, in literally 5 seconds, give you a D, a fake D, but an alternate version to C. What I'm saying here is, if this problem had been this, if C had been this way, if I had asked for the inverse sine of negative square root of 3 over 2, then this answer would have been negative pi over 3. That's for inverse sines only. I'll give you a special case of that rule for inverse cosines, not today, but it does give you kind of an easy way to do things. Actually, on that note, let's go ahead and call it. No, we are going to do D. I'm sorry, I have enough time. I was looking at E, and I was thinking I didn't have enough time. But I should be looking at D, shouldn't I? Inverse sine of negative 1/2. So what we're doing is we're trying to find some angle so that the sine of that angle is equal to negative 1/2. These are the same problems, just without restrictions, but we know that this is restricted to the negative pi over 2 to pi over 2. And I'm going to write it in interval notation this time. Well, we can just delete the negative and call it a reference angle. So that means the theta prime would go here. It would have an opposite of 1, a hypotenuse of 2. That's the 1, 2 square root of 3 triangle. And that says that theta prime, that's opposite the 1, is the 30 degrees, which is pi over 6. But this is supposed to be negative. Sine's negative in quadrants 3 and 4. But we don't include quadrant 3 because inverse sine is restricted out of quadrant 3. We only include quadrant 4. So we put the theta prime in quadrant 4, but using all that stuff, not calling it 11 pi over 6, that would be outside of the restrictions. We have to call it negative pi over 6. So I verbalized all the different details there, but also, I mean, if this was a negative, this is a negative. That's it's easy as it gets with sine and its inverse. All right, so we're going to stop there. We will do 3 or 4 more, 2 to 4 more next time. We'll also introduce the inverse tangent. We'll also introduce a much more complicated type of problem involving this. And then we'll show what the simple homework problems from 5.2 and 5.3 were, word problems where you're trying to find an angle given like an opposite and a hypotenuse or an opposite and adjacent. And it's just as easy as using a calculator. So we'll share that next time.
All right, before we continue where we left off, I wanted to point out that you might see something about test one being on like an October date once or twice in the middle of this video. Like I've said in the past, when I'm recording stuff, quite often I just accidentally leave that stuff in there because I'm looking at it and making my notes and everything. So if you do see it, again, just ignore it. Clearly, that is not for us. The appropriate due dates for our class are always listed at the beginning and end of each lecture. But again, let's pick up where we left off.
Iterate where we were in 5.7. Inverse trig functions. So we related the idea of an inverse function and it being an invertible function that it had to pass the horizontal line test. And that enabled us to build our inverse trig functions. Remember, these are not being raised to the -1. This is not 1 over sine x. And if I didn't say that last time, make sure you understand that. This is not 1 over sine x. This is inverse sine x. I know it looks just like it would be 1 over sine x. 1 over sine x would look like this. Go. Stop that. Thank you. Oops. This would be 1 over sine x. It would have to have parentheses around the trig function and the -1 that way. With the -1 here, that is what denotes that it's an inverse function, not a reciprocal. So there's a giant distinction between those two things. So in fact, sine of x raised to the -1, which is 1 over sine x, is actually the same thing as cosecant. So sine x raised to the -1 in this manner is cosecant. Sine x with a -1 in the middle sandwiched like that has nothing to do with any of that cosecant jazz. It's saying we're swapping the idea of what's the x's and what's the y's. So we also discussed how we had to really limit the window of your sines and cosines because of how they are. They wave around like this. So to pass the horizontal line test, it's going to fail miserably in this way. So we had to trim it down immensely. And we ended up having to trim it down from -pi/2 to pi/2 in terms of x, or the domain of the regular function, which means the range ended up being -pi/2 to pi/2. Whereas the range of the regular function being -1 to 1, now the domain of the inverse function is -1 to 1. We took that same idea and spun it for the cosine, showing that we had to actually restrict it from 0 to pi. I know it's annoying that these trig functions, they always have these subtle differences between them. Sine and cosine waves look almost identical in the grand scheme of things, but one of them starts at a height of the amplitude, the other starts at 0. One of them, when you invert them, you have to do it this way. One of them, when you invert it, you have to do it this way. And again, that's just to make sure that you're not bumping into it more than once with their horizontal lines. There we go. We showed the graphs of the inverse functions. We explained kind of the reasoning as to why they loop around in opposite directions, because remember, an inverse function, the idea is you're swapping x and y coordinates. Bigger picture, it means you're reflecting across the line y equals x. So if you put, let's just do the sine function. Here's your sine of x. Then, if we flip that about the line y equals x, what we get is this. And I drew that terribly. In fact, the blue line is what's drawn terribly. So let me just do that a little better. Almost looks like a DNA strand, but only part of one. And that's that. So regular function, you can find the inverse function by just treating this y equals x line as a mirror. Nobody really does it that way, though. We just say swap the x and y coordinates because that's a much easier concept. But that proves that the bending should be this way, whereas last time I just kind of argued reasons. Now I visually show it. I did mention that I'm not really going to test you on the pictures of the inverse sine and inverse cosine functions. This does come up in calculus, though, so I'm not saying you'll never see this again. You will see this again at some point. But we don't deal with it too much in regular trig. So what we spent time doing is finding inverse sines of something. Now remember, when you're an inverse sine for a sine of something, it's sine of an angle ends up equaling the opposite over the hypotenuse, or if it's cosine adjacent over hypotenuse, etc. So the inside was the angle, and then this right side is your ratio. But when we have inverse sine of something, the inside of this is supposed to be the opposite and hypotenuse, and then what it equals would be the angle. These are flip-flopped. So we said, okay, this black inverse sine of square root of 2 over 2 is really just saying the same thing as this. Find an angle such that the sine of the angle is square root of 2 over 2. Some people will do this rewrite, some people will not. That's up to you and how much practice you do and how much you feel you need it. But remember, these inverse trig functions have massive restrictions. The inverse sine is restricted between quadrants 1 and 4 because this goes from negative pi over 2 to pi over 2. And we talked about how you can't even use angles like 3 pi over 2 or 11 pi over 6 because that's not in this actual window. Those would be up here in relation to this graph. So we had to turn them into, instead, rotate clockwise and get negative angles. That's not going to be an issue for the inverse cosine because inverse cosine goes between 0 and pi, which is in quadrant 1 and 2. So they both have their complications. They both have little details you're going to have to memorize. This red ink was me saying back in 5.2 or 5.3 before we talked about inverse trig functions, this is what I would have asked, where you find all the different angles and you'd end up with 2 answers. But these inverse trig functions, they generally are only going to have 1 answer unless it's something weird or wacky that, spoiler alert, won't happen on the first test or the first series of homeworks. We did another one. The first one we had to use a right triangle. The second one we ended up using the quadrantals. The third one was more similar to the first one. Yeah.
Got to do a quick edit.
Actually, inverse cosine of square root of 2 over 2. Now, first of all, I'm going to say that this is the same as finding the inverse cosine of 1 over square root of 2. This is something that you've got to get used to understanding and seeing, because we don't memorize this triangle with square root of 2 and 2. We memorize it with a 1, a 2, and a square root of 3, or not this triangle, but the 45, 45, 90 in particular. So you need to remember that these two numbers are the same thing, and we end up having to rationalize denominators so much that I hope that you do. Pattern recognition is important. So that means we are really trying to find an angle such that the cosine of said angle is equal to 1 over square root of 2, or 2 over square root of 2. I'm sorry, square root of 2 over 2. The black version or the blue version, whichever you like, but I prefer this one. But it can only be, we can only consider quadrant 3 and 4. What am I saying? What am I saying? I'm thinking one step ahead. It's quadrant 1 and 2. It can't be in quadrant 3 or 4. That was because, I'm not scrolling, there we go. The inverse cosine is only valid between 0 and pi. 0 and pi are quadrants 1 and 2. 0 to 90 is 1, 90 to 180 is 2. So inverse cosine is only valid in quadrants 1 and 2. Now, when you're dealing with the positives, the cool thing is it won't matter whether it's an inverse sine or inverse cosine. You'll get lucky because both of them, any positives go for quadrant 1, but the negatives for the inverse sine go to quadrant 4, not 3, where it would also be valid the other way, the simpler way. Inverse cosine is positive in quadrant 1 and 1 and 4, so negative in 2 and 3, but you only consider 2, not 3, again, for the reasons we've discussed. We had to trim it up. This is only valid from quadrant 1 to 2. So positive answers, you use the angle in quadrant 1. Negative, it depends if it was inverse sine or inverse cosine. How can you remember that? So is it just blind memorization of this fact? Doesn't have to be. What you can do if you're stuck, and this is exactly how I do it, and I'm telling you, your teacher does not just blindly memorize factoids like this. I hardly ever do things that way. I rationalize them. So if I have a test, what I do is I draw my sine and cosine graphs, and I figure out how they're supposed to be chopped up on the fly. I do my horizontal lines, and I chop them up. So this, if I was the student taking the test, I would have literally done this stuff to figure out, all right, well, here's my sine wave, but how do I need to chop this up to make sure it's invertible? Well, this is how. So that tells me I got to use quadrant 4 and quadrant 1, because we're going from negative pi over 2 to pi over 2. And then I draw my cosine wave, starting at a height of 1 and waving, waving, waving. And I go, well, no, I got to chop this up, and then this is how I chop it up. So I only use quadrants 1 and quadrant 2. That's what I would do if I were the student, instead of just blind, blatant memorization. Do you have to do it that way? No, that's up to you. All right, back to the point, back to the problem. So we're trying to find an angle such that the cosine is 1 over square root of 2. Well, we could use our board sheet thing, but I'll just redraw the triangle real quick. Now this is positive, so it is the actual angle, not a reference angle. The adjacent is 1, the hypotenuse is the square root of 2. Well, this is the 1, 1 square root of 2 triangle, which says that the angle has to be 45 degrees, which is pi over 4. That's the answer. No negatives, no problems. If the original arguments were positive, with inverse trig functions, the answer goes in quadrant 1. Easy peasy. Let's do one more. Switch back our color to black, though. Draw black. Here we go. F. Inverse cosine of negative square root of 2 over 2. So we're trying to find an angle. Now this square root of 2 over 2, same thing as last time. So I prefer to say this is the same as saying the inverse cosine of negative 1 over square root of 2, because that'll make it easier for me to associate the correct triangle with it. All right, so what we're doing is finding an angle such that, so the cosine of said angle is -1 over square root of 2, but we only consider quadrants. Which ones? Is it 1 and 4 or 1 and 2? Now you might be wondering, how do you know it's 1 and 4 or 1 and 2? Why not quadrant 3? Quadrant 3 is never, ever, 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 ever used for inverse trig functions. Because you need this smooth, continuous graph for your inverse trig functions. So you only end up ever using 2 quadrants. So to do this, it's quadrant 4 and 1. To do this, it's quadrants 1 and 2. The only way you could use quadrant 3 is if you were going in quadrants 4 and 3, which you would never ever do. You always want to use quadrant 1 and then whatever is next to it. So quadrant 4 is next to it, quadrant 2 is next to it. So it's one of those. Don't ever put it in quadrant 3 for inverse trig functions. For cosine, well, cosine, so this is the way I do it on a test. All right, what's cosine wave look like? We start at a height of 1, and we do, that was poorly drawn. We do this, and it goes forever in each direction, where we know that this would be pi. Okay, well, this is going to fail the horizontal line test, so you have to trim it up, and you end up trimming it between here and here to make sure that there's no overlap. If you keep going, you'd fail the horizontal line test. So that tells me I'm between 0 and pi, and then I know, hey, I'm only using quadrants 1, 2, not 1 and 4. All right, so we'll draw up our triangle, but because there was a negative involved, that makes this a reference angle. The opposite, sorry, the adjacent should be the 1, the hypotenuse the square root of 2. It's the 1, 1 square root of 2 triangle again, which says that theta prime is pi over 4. But we need to put this in quadrant 2. So we draw the angle in quadrant 2. Here's our pi over 4. That's our reference angle, which means we're trying to figure out this angle. This is our true theta, which would be pi minus pi over 4, or 180 minus 45 degrees, whichever way you need to do it. So theta would be equal to pi minus pi over 4, which is 4 pi over 4 minus pi over 4, which is 3 pi over 4. Just making that minus a little clearer. There we go. So that's our answer. Theta equals 3 pi over 4. So I gave you a helpful little memo earlier for the sine, technically last class. If the inside of an inverse sine is negative, the answer will simply have a negative answer. That's not the way it works for the cosine, though. So that little memo here is the inside of an inverse cosine is negative. The answer is in quadrant 2, and theta should be equal to, I'm going to write that part out. Pi minus the reference angle. That's the little shortcut sheet, whatever you want to call it, if you like to use that. Okay, so those are our inverse sines and cosines. Now we're not done with those. We will come back to those later in this section when we make things a little more complicated. You're probably wondering, how in the world are you going to do that? Isn't this bad enough? Well, we're going to start stuffing one thing inside of another thing. We're going to start doing composite trig functions. Oh boy. But you have to be careful. You can't just stuff a sine inside of a sine. You can put sines inside of inverse and inverses inside of sines, but you can't do an inverse in an inverse or a regular in a regular. You'll see what I mean later. For now, let's get to talking about the tangent. Y equals, and I'm going to skip the graphical rationalization of this one, but y equals inverse tangent, sorry, y equals regular tangent of x must be restricted 2. Negative pi over 2, comma pi over 2. In parentheses, though, to be invertible. I have 2 twice, don't I? There we go. It still doesn't like it, whatever. Ignore, where's ignore? Where's ignore? It just went away on its own. I love technology. All right, so again, skipping the graphical part just in the interest of time. Actually, I'm lying. I'm going to show it below. I'm lying. Sorry, hold on. Give me 30 seconds. All right, sorry, I dropped my notes for today's class, not for this part. So regular tangent graph is what we're trying to draw. So remember, it looked like a cubic, and it had asymptotes between negative pi over 2 and pi over 2. So if we drew this thing forever and ever and ever, it would just kind of look like this, and then another one, and another one. And you can see that this would fail the horizontal line test miserably. So you got to trim it down. So what you do is you just use this. That section right there would be the perfect trimming, because it will pass the horizontal line test if you ignore my poor artistic ability where it humped over right there. So that's the reasoning that we restrict the tangent to negative pi over 2 to pi over 2. This is the same restriction. Actually, let me be a little more specific. This is almost the same restriction as sine. This is the restriction for tangent, where negative pi over 2 to pi over 2, but surrounded in parentheses. Let's look at the restriction for sine, though. Sine was restricted to negative pi over 2 to pi over 2, but it had brackets. It had brackets around them instead of parentheses. Why is that? Why did we have brackets for that one? Well, because these points were included. We'll have parentheses for this one because this negative pi over 2 and this positive pi over 2 are asymptotes and have to be excluded. That's why we use parentheses there, due to the asymptotes, the asymptotes. That is the only difference between this and a sine. So sine and tangent are close to each other at least. Cosine's the odd man out that goes from 0 to pi. Sine and cosine use brackets, tangent use parentheses because of asymptotes. All right, so with that in mind, y equals, I'll write it out. Y equals inverse tangent of x has a domain of negative infinity to infinity and a range equal to negative pi over 2 to pi over 2. Remember, regular trig function's domain becomes the range of the inverse function. Regular function domain becomes the range. Then the regular function's range becomes the domain. I never wrote the regular function's range, but you can see it. It goes up forever, it goes down forever. So this right here, excuse me, was the range of just a regular y equals tan x, not an inverse function. So that was the range of tan, so it's the domain of inverse tan. And then I'm going to go ahead and make the memo for the, what quadrant is it in if there's a negative argument. If the inside of an inverse tan is negative, then the angle is simply negative. Notice this is the same as inverse sine. Argument. Literally the same argument as the inverse sine. So inverse cosine is kind of on its own island. I really don't do a lot of inverse tan functions. They're not nearly as interesting. So let's just do one of them. What example are we up to? 2? It's got to be 2. Yes. So example 2, evaluate. This is just going to be y equals inverse tangent of -1. Now remember, when you're looking at inverse trig functions, the inside is supposed to be the ratio of opposites, adjacents, and hypotenuses. For a tangent, that should be the opposite over the adjacent. That's what the inside should be. It should be an opposite over adjacent. But it's not written as a fraction, it's written as a whole number. So what you might want to just say is this is the same as y equals inverse tangent of -1/1. That helps a lot of people. So what we're trying to do is we're trying to find an angle so that or such that the tangent of said angle is going to be -1/1. Inputs and outputs are swapping when you go to the regular function. But we only, looks like a bot, but we only consider definitely quadrant 1, but what's the other one? Is it 2 or 4? Is it 2 or 4? Well, remember, tangent had this look, and we were asymptoted, and we had to go to the left, so that meant we're going between -π/2 and π/2, which is quadrant 1 and 4. Why did I write 2? 1 and 4. All right, so let's set up our, because this is -1/1, let's set up a reference triangle. So this will be our theta prime. The opposite will be the 1, the adjacent will be the 1, this will be a square root of 2, and that instantly says that theta prime is π/4. Because you have memorized that triangle, or you've just memorized blatantly the fact that the tangent of 45 degrees is 1/1. It's up to you how you're doing the things, but I've given you multiple ways to do them. All right, so since the angle is supposed to be negative because of that, that just says theta is equal to -π/4, based on that memo I mentioned earlier. If you don't believe me, if you don't trust the little memo right here, what you do is you draw this angle, but in quadrant 4. And when you draw π/4 this way, you just rotate clockwise to get -π/4. Remember, you don't want to go counterclockwise because that would give you a, was that 7π/4, which is outside of the range. So that's just a clockwise rotation of the same angle. All right, let's keep bumping this down. Sure. Now, what we're going to start studying for the final bit of the section, composite trig functions. Composite means one inside of the other. So a sine inside of an inverse cosine, or an inverse tangent inside of a cosine, or a secant inside of an inverse secant, or a sine inside of an inverse sine, or an inverse sine inside of a sine. But the trick there, and it's not a trick that you have to know, you can only be given this style problem. You can't be asked what's the cosine of pi or something like that. It doesn't work. You can't take the cosine of something, because remember, when you spit out the cosine of an angle, you're getting a length, a ratio of lengths And then if you try and take the cosine of a ratio of lengths, that literally doesn't exist. You can only take the cosine of an angle. So you will only see problems where, for these composite functions, one will be an inverse and the other will not. The inverse could be inside or it could be outside. Doesn't matter. They could be the same type of trig function or they could be different. It doesn't matter. But when they are the same type of trig function, sometimes you get some really easy cases, and that's what we're about to detail. Angle is part of the range of the inverse function. Then you can say, I almost want this to go down the line, that the inverse sine of a regular sine of an angle is equal to the angle. Or, same thing, if the angle is part of the range of the inverse function, then you can say the inverse cosine of the cosine of an angle is just equal to the angle. Or, if you have, I think you're know where I'm going with this, the inverse tangent of the tangent of an angle, that would be the angle. The idea here is that inverse sine and sine cancel, inverse cosine and cosine cancel, inverse tangent and tangent cancel. In the same way that if you have x plus 5 equals a number, you subtract 5 on both sides to cancel. Addition and subtraction are inverses of each other. Multiplication and division are inverses of each other, so they cancel each other. Square roots and squares are inverses of each other, so they cancel. A function and the inverse function are literally inverses of each other, so they cancel. And in all those ideas, when you cancel, you're left with the base argument. With trig functions, it's the angle. But there's a special condition for this. And that is if the angle is part of the range of the inverse function. This is not always the case. So inverse functions only work if you're actually in the appropriate values. So if you're dealing with an inverse sine, you're only good with values in quadrants 1 and 4, and the quadrants in 4 have to be just the negative versions of quadrant 1. If you're dealing with inverse cosine, you're only valid in quadrant 1 and 2. My point being, if I asked you the inverse sine of something where the angle is in quadrant 3, you couldn't just say they cancel, you would actually have to work from inside out. So that is a very important detail. Yes, in general, up to this point, all inverses and regular things have canceled with each other. Addition and subtraction canceled. Multiplication and division canceled. Square roots and squares canceled. But in trigonometry, because we had to narrow the windows so much to half of a circle, not even a full circle, that means that these two don't always just cancel each other out. Sometimes the angle that's the answer would be different from the angle that was in the argument. So you have to pay attention. Oops. Type, please. Thank you. So if this is not the case, why did my font size changed? Why did my font size change? Either way, if this is not the case, you work inside out. Just like with composite functions, because that's literally what these are. So if the angle is not inside of the range, you have to work them inside out. Also, if these functions don't match, by match, I'm putting it in quotes because they're never going to literally match. I mean, you have a tangent and an inverse tangent, or a sine and an inverse sine. What I'm saying is if you had an inverse cosine of a sine, so if they don't match, you must work inside out as well. So that'll bring us to example 3. Evaluate. And for A, we're going to have the inverse sine of the sine of pi over 4. Now you might be thinking, well, could you do the sine of the inverse sine of pi over 4? The answer is no. You cannot do the sine of the inverse sine of pi over 4 because with inverse trig functions, the inside argument must be ratios of opposites and adjacents, something like a half or square root of 3 over 2. So no, you can't just willy-nilly flip these and leave the pi over 4. It would have to go in this order. If I wanted to do a sine of an inverse sine, it would be something like, I'm not actually doing this, inverse sine of maybe a half. We'll be doing problems like this in example 4. Don't worry. So when it's an angle, it has to be sine of an angle. Okay, so inverse sine of pi over 4. Well, these two are the quote same, they match, they're inverses of each other, which means maybe we'll have this special case. If the angle is part of the range, then we can just say the whole thing would be equal to pi over 4. Don't assume though, make sure it's right. So pi over 4 is in which quadrant? Quadrant 1, which is valid. Or inverse sine. Inverse sine is valid in quadrants 1 and 4. So this is fine. So we can just take that quick little cheat and say, so the answer is equal to the argument of pi over 4. Easy peasy. Spoilers, b might not be the same. Let's do the inverse sine of the sine of pi. So pi is between quadrant 2 and 3. Now, if we were talking about pi over 2 is between quadrant 1 and 2, but it is the edge of where inverse sine is valid. It's valid up to pi over 2, so that'd be fine. Pi is way outside of that range. This is not valid for inverse sine. It wouldn't even be valid. I'm sorry, I was about to say something wrong. This would be valid for inverse cosine. We can go from 0 to pi for inverse cosine, but we go between negative pi over 2 to pi over 2 for inverse sine. So if I switch these sines to cosines, the answer would be pi. But it's not. They're sines. We're not in that valid window, which means we have to work inside out. So the first thing we do is find out what is the sine of pi. Just focusing on the inside. What is the sine of pi? Well, that's a quadrantal, so you go to your unit circle. Pi is 180 degrees. That point, I'm going to erase this after I draw it up. 180 degrees would be this point right here, which is negative 1 comma 0. The sine means we're taking the y value, so we're taking the 0, which is 0. So the sine of pi is equal to 0. So sine inverse of sine of pi, I'm just writing blue so you can see the direct substitution. This will now be the inverse sine of 0. Now this 0 is not an angle. This is not 0 radians. This is the ratio of 0 over literally any number. So what you're asking here is, we're trying to find the inverse sine of 0. So what we're saying is, find an angle so that the sine of that angle is equal to 0, but we're only between quadrants 1 and 4, up to their borders. There are two values of which the sine of an angle is 0. If you go to that unit circle, let me pull that up now. I don't want to have to keep redrawing it. That's the wrong class. 162, board cheat sheet. So here's our unit circle. So we're trying to find where is the sine equal to 0. Sine is the y value, so we're looking for y values that are 0. Here is a y value that's 0, and here is a y value that's 0. But we've already talked about how 180 degrees is outside of what we're supposed to be looking for. For an inverse sine, we're not looking at this side at all. It doesn't exist for an inverse sine. We're only looking at this half circle. So that means 0 degrees or 0 radians is the only angle. There's not two answers, and that would be the answer. So theta equals 0. So that means the inverse sine of the sine of pi is equal to 0. That's the answer. It was not equal to pi. Again, because pi was outside of the window. Now anybody be saying, well, since it was outside of the window for inverse sine, you don't even do it. Well, it doesn't matter because inside of here, we're not even looking at the inverse sine. Pi is perfectly fine for a regular sine. So that's not an issue until we go outside of it. But outside of it, we've already turned that into ratios of sides. So it's irrelevant where we started. This is one of my favorite types of problems because it really emphasizes that while inverse functions generally cancel each other out, there's special types of inverse functions with very, very narrow windows, which means they don't always just cancel each other out, so you got to work inside out anyways. It's annoying, it will frustrate you, but it's important. All right, last set of examples for the section. Example 4, evaluate. A. Now let's start mixing them up. So for these 4 problems, I'm going to switch the order of inverse and regular function, but it doesn't have to be that way. I can still ask what's the inverse cosine of the sine of pi, or what's the inverse tangent of the sine of pi over 4. I can certainly do that. And again, you're just working inside out. That's the core idea of these problems. If they don't match, work inside out. Do the inside problem on its own, then do the outside problem with the new information that you have. So for A, we're going to do the sine of the inverse tangent of 7/24. Sine of the inverse tangent of 7/24. First thing you might think is, we haven't dealt with any triangles with ratios of 7 to 24. How am I supposed to know if this is 30 degrees or 45 degrees or 60 degrees? Well, guess what? It's neither of them, or none of them, since it's 3 options. And it's definitely not a quadrantal. So then you're going to go, well, Mr. Beckner, you never told me to memorize all these other angles that have ratios of opposites and hypotenuses of 7/24. Here's the cool thing. I didn't ask you to do that because you don't have to do that. It has nothing to do with this problem. You're never going to find the angle of this. You're just going to use the angle, build your own right triangle, and find the answer from there. So you'll just have a theta written somewhere. You'll never actually determine it. I never asked for an angle. I asked for the sine of an angle. This right here, wrong color. This right here is the angle. So we just want some sine of theta where the theta is bound by these values. So again, the first thing you need to do is find out what is the inverse tangent of 7/24. It's equal to some angle. So we're finding some angle so that the tangent of it is equal to 7/24. Again, if you don't need to do this rewrite, that's up to you. I know not everybody does. I personally don't, but I've done this a lot. I definitely did it at first. All right, well, how do we find this? Well, that's an opposite over an adjacent because SOHCAHTOA. That's another thing, if you don't memorize, you're going to regret it all semester. So let's just draw a right triangle where our angle's here. TOA, T-O-A, so the opposite is the 7, the adjacent is the 24. And then this would be our hypotenuse. We can label it C if we like. And then we can find that based on Pythagorean. So we know that C is going to be the square root of the A squared plus B squared. I'm not going to rearrange the formula for the 10 millionth time. So that'd be 7 squared plus 24 squared. Spoiler alert, when you do all that arithmetic, I'm going to entrust you to do it. You're going to get 25. But 7 squared is 49. 24 squared is what's that, 576. And then 576 plus 49 is 625. And the square root of 625 is 25. So that tells you what your hypotenuse is. So now if you really wanted, you can redraw the triangle. 24, 7, 25. Ooh, it's got nice pretty whole numbers. There aren't a lot of triangles built that way. We have the 3, 4, 5 triangle. We have the 5, 12, 13 triangle. There's the 7, 24, 25 triangle. There aren't, I think there's only one more, and I don't know it off the top of my head, where it's only using single and double digit numbers and they're all whole. It's a pretty rare instance. Yes, there are multiples of those 3 base triangles, but they all are just multiples. Like 3, 4, 5 means there's also a 4, 6. I'm sorry, I said that wrong. 3, 4, 5 means there's also a 6, 8, 10. You can just double the values or triple the values or quadruple the values. All right, so while we can't actually find out the angle, we can't find theta literally without a calculator. I would need a calculator to find out this angle, which I'm going to start showing that, I guess, after this problem. I was going to wait till the last 4, but it's relevant now. We can't find the angle, but that's okay. We don't care. Just call it theta. So the theta is bound to the fact that its inverse tangent is 7/24. So the sine of inverse tangent of 7/24 is the same thing as finding the sine of what we're calling theta, where theta is based on this right triangle, this one more specifically. So the sine of theta just says to go to this right triangle and do its opposite over its hypotenuse. So this would be equal to, the opposite is 7, the hypotenuse is 25, so the answer is 7/25. That's it. That's an ugly 5. The sine of that angle is 7/25 based on the triangle we drew up. So we're just asking for the sine of the angle, which was the sine of the inverse tangent. Again, don't try and look at this all at once. Don't look at this all at once. It's a terrible idea. Focus your field of vision to just the inside, which for an inverse trig function, very often you're drawing up a little triangle for that, even if the numbers aren't numbers you've seen before. And then when you do the outer trig function, you're generally just referring to that triangle. If we did this the other way, if we were doing the tangent of an inverse sine, and again, this would now be an angle I'd have to write. I'd actually have to write an angle, which means I'd have to use angles that we're used to, which is why we're much more limited, and generally the problems are like this, which is why I do them this way and not the other way. Okay. B, cosine of the inverse sine of a half. This time we got about 15 minutes. Should be just enough time to finish this section, I hope. Oh no, I said I was going to do something, didn't I? Before we do that, calculator. So this was an issue that would have come up for a word problem or two. And yeah, let's get radians for now. That I said I was going to come back and approach, and I was going to do it at the end of this section, but I might not have time today now that I'm running short. Shoot. Either way. So the inverse tangent of 7/24. We literally never said what it was. We just said that it means we're forced to this right triangle. That would tell us everything about the inverse tangent of 7/24. If you wanted to find that in a calculator, look where my mouse is, if you can see that. Here's the tan button on a TI-83. The inverse trig functions are usually on the same button, and you hit second and then that to get to it. So I could do second tangent of 7 divided by 24. And this answer would be in radians because I'm in radian mode. So in radians, that's 0.283. And that means nothing to you probably. So let's change our mode to degrees just so we have a better grasp on it. And let's do the inverse tangent of 7/24 again. And it says it's about 16 degrees, 16.3 degrees, rounded to the nearest tenth. Okay, Well, that's cool. So it's about 16.3 degrees, and then the sine of that turns out to be 7/25. But if we did it this way and then try to do it, if you do this, the sine of the inverse tangent of 7/24, so if you just plug this in a calculator, you get 0.28. Okay, but why is it 0.28? And if you wrote 0.28, I think my math lab wouldn't even like that, because it would want this as a fraction since it could get converted, and typically we use fractions, not decimals, when we're talking about ratios of opposites, adjacents, and hypotenuses. So don't think your calculator is going to do everything for you. First of all, this is a no calculator test. You're not even supposed to be using this. Second of all, inverse trig functions in calculators are very wacky when you're using them, because the calculators have the issue of they're not always sure about the quadrants. So you might do a sine of an inverse trig function and you get something and it's supposed to be the negative of that. Or you get a negative and you were actually supposed to have the positive of it. So you just have to be careful. Inverse sine of the sine of pi. Sure, I'm modes in radians again since I did it that way. See, that's right, but there's always a possibility that it's wrong, and I'm not going to show any right now, but please trust me that they can be wrong if you're dealing with anything that might have quadrant 2, 3, or 4 involved. All right, now on to B. Cosine of inverse sine of a half. So the first thing you want to do is you just argue the inside, and the inside's supposed to be an angle. So first, we say that the inverse sine of a half is equal to theta, or x, or whatever letter you like. It doesn't matter. I just like theta. So that means we're finding theta so that the sine of theta is equal to a half. Well, that's a very well-known triangle, but of course we're restricted to the quadrants. We're dealing with inverse sines, so quadrants 1 and 4 only, but this is positive, so that won't be an issue. When you draw your little triangle, here's your angle, 1, 2, square root of 3, which says that your angle is actually pi over 6, excuse me, but we don't actually need this. We didn't need it in the last problem. And what I mean by we don't need is we don't need to know the actual angle. Even though, yes, it is pi over 6, I don't actually need to know that. I can still just call it theta. So I can go for the second phase. When we're doing the cosine of what I've called theta, I don't even need this. I can completely ignore the fact that it's pi over 6, and I could just go, oh, well, cosine is the adjacent over the hypotenuse, so it's square root of 3 over 2. I didn't need to know that it was pi over 6 this time. It's very rare you don't need to know that. And that's by, again, this triangle. Again, did not actually need to know that fact. It's good to know, but I didn't need it. So that says the cosine of the inverse sine of a half is equal to square root of 3 over 2. That's the answer. C. The secant, of inverse sine, right? Yes. Of negative 1/2, negatives, secants and negatives, oh boy. Oh, first thing we do is we're just considering the inside. We're trying to find the inverse sine of negative 1/2. Inverse sines, inverse trig functions are angles, so let's call it an angle. Which really means we're trying to find an angle such that, or so, the sine of that angle is negative 1/2, and we're limited to quadrants 1 and 4. We'll have to be in quadrant 4 because it's negative. Oh, but sine is negative in quadrant 3. Doesn't matter. Inverse sine is not valid in quadrant 3. No inverse trig function is valid in quadrant 3. All right, so that means we can just draw up a reference triangle with an opposite of 1, a hypotenuse of 2, and that means the adjacent square root of 3 again, which says our reference angle is pi over 6. Again, I don't actually need to know that. But it would be tougher ultimately without knowing it for a couple of reasons. If the reference angle is pi over 6, that means the actual angle is negative pi over 6. And that's why I'm going to say it's slightly more important, not necessarily to say that it's pi over 6, but the fact that it is negative, which puts us in quadrant 4. Three exclamation marks, because we're going to be taking the secant of something in quadrant 4, which means we could screw up the plus or minus aspect if we're not paying attention to those great details. So now, second of all, we're doing the secant of what we've decided to call theta. Yes, it's negative pi over 6, but really we're just using this triangle and the fact that it's located in quadrant 4. I didn't need to say all of this. I just know it's in quadrant 4, which means that angle would have been negative. Okay. So the secant of that angle, well, secant is 1 over cosine, if you prefer it that way. If you don't, then don't change it. Secant is 1 over cosine. Cosecant is 1 over sine. So cosine is adjacent over hypotenuse, which means secant is hypotenuse over adjacent. So we're doing hypotenuse over adjacent, which is 2 over square root of 3. So this would be equal to plus or minus 2 over square root of 3. I've got the plus or minus because we're in quadrant 4. We have to make sure we get this right. In quadrant 4, secant, which relates to cosine. All right, quadrant 4 means we're going right. Cosine is an x value, which means we're going right, which means it's positive. If this had been a cosecant, which would relate to sine, quadrant 4, sine's negative, so we'd choose the negative instead. So the secant of this angle is equal to negative 2 over square root of 3. But you're going to be slightly annoyed. There's one final detail we have to account for. We got to rationalize the denominator, multiply top and bottom by square root of 3, giving us a final answer of negative 2 square root of 3 over 3. Why did I say negative? I said to choose the positive and then I wrote a negative because I got so focused on that sign, excuse me. Erase the negative, erase, you silly computer. Erase the negative. We chose the plus. I said it, I wrote it. Be consistent. So 2 square root of 3 over 3 is the answer. This is one that a lot of people would think the answer is negative because this inverse sine had a negative. Oh, so just give the secant a negative. Nope. Because sine is negative in quadrants 3 and 4, but secant is negative in quadrants 2 and 3. These subtle details will make or break you. All right, D, last one. Tangent of the inverse cosine of negative 3 over 7. Again, the first thing you do, focus on the inside. Inverse cosine of negative 3/7. Sorry if my audio is a little unstable. It just told me my internet connection is unstable. Remember, recordings are always fine. So if this is buggy, go back and watch this last part later. All right, so remember, we're calling this an angle, which means we're trying to find an angle so that the cosine of the angle is equal to negative 3/7. But we're restricted to quadrants 1 and 2. If it's negative, it will be in quadrant 2. Remember, we're restricted to quadrant 1 and 2 because we talked about an inverse trig function. If I never mention inverse trig functions, and I don't just blatantly say there's restrictions, then there's no restrictions. All right, 3 and 7, we definitely haven't made a triangle out of that, so let's make a triangle out of that. Because we're in quadrant 2, I'm going to call this a reference angle. Cosine is adjacent, so here's the 3 over hypotenuse, here's the 7. Let's call this B, and we can find it based on Pythagorean. B, again, you can rearrange the formula on your own, ends up being the square root of 7 squared minus 3 squared, which is 49 minus 9, which is the square root of 40. Which would be the square root of 4 times 10, which would be 2 square roots of 10, when you reduce it as much as possible. That triangle is really the 3, 2 square root of 10, 7 triangle. I have no idea what that angle is. You will have no idea what that angle is. Don't put it in your calculator because I don't care what that angle is. We're just going to be using this to build the tangent. But remember, this is theta prime. We're really supposed to be noting that this is in quadrant 2. Because the cosine was negative, that means we're going left, either quadrant 2 or 3, but inverse cosine is not valid in quadrant 3. So make sure you're considering that when you do your tangent. So now, oops. Now what we're doing, or second, now is probably a bad word choice for later, now and later. All right, we've got the tangent of the angle. The angle is based on that triangle. The tangent would be opposite over adjacent. So it's plus or minus 2 square root of 10 over 3. Since we're in quadrant 2, tangent is negative. So we choose the negative one. So the tangent of our angle is negative 2 square root of 10 over 3. And that is our answer. That's what the original problem is equal to. So many students will forget this negative and the whole thing's wrong because of that. And then you go, hey, Mr. Beckner, check me for partial credit on this question. And I go, you didn't show your work, no credit. If you did show your work, then I'll go, okay, yeah, you'll get 4 to 5 points or 3 to 5 points, some tangible, pun intended, amount of points. All right, that technically closes the section, but I want to do one quick thing that I kept mentioning last class and today. I have just enough time. Previous word problems, IOUS. And 5.2, 5.3 might have been something like this. Bob is doing physical therapy. And he's laying flat on the ground and he's trying to lay his arms flat. So he takes his arms, which are initially pointing straight up. He's holding a bar and he's using one of his arms to bend behind his head. And he manages to drop his arms as low as possible. He knows his arm is 2 feet long. And his friend manages to measure the lowest height he can achieve at 0.3 feet. What angle does his arm form against the ground? So here's what I'm saying. This is the image. And they basically draw these images up for you anyway. So he's pretty low at this point. So this right here is his arm. This is the, let's say it's not right at your shoulder. It's in your armpit, but that pivot point might be a little just off center. Don't worry about it. But that's his arm, which we said was 2 feet long. So he's got a 2 foot long arm. Then he's got a friend who manages to measure this distance, the vertical distance from where his hand is. So this right here is his hand or the tip of his finger. Hand, finger, whatever. And then this was 0.3 feet. I didn't want to do it in inches because I don't feel like converting units. And they say, what angle does his arm form against the ground? So that's the angle right here. We don't know this horizontal distance. Guess what? We don't need to know this horizontal distance. Yes, we could find it by Pythagorean, but we don't need it. So I did some word problems like this previously, and we said, you want to try and use a trig function where you're going to use 2 of those quantities, or if one of these was unknown, then you try and use at least one of them. So we know the opposite, and we know the hypotenuse. What trig functions use opposite and hypotenuse? Sine and cosecant. Let's not use cosecant because it's the one that's, goofier. So we're going to use sine. So we would say the sine of that angle is equal to the opposite of 0.3 feet over the hypotenuse of 2 feet. Well, guess what? This is exactly like an inverse trig function. So this would be the same as finding the inverse sine of 0.3 over 2. That would be equal to our angle. We just spent the entire class going from the blue to the black. Now we're going from black to blue. Well, this is an application, so we're definitely just putting this in a calculator. They're all positive because we're not going to deal with negative links in terms of geometry. So we pull out our calculator. Now, if you want the angle in degrees, let's check our mode. We are in radians currently, so let's go to degrees. This would probably be a little more relatable. Pay attention to what my math app wants the answers format as. If it wants radians, leave it in radians. So we're going to go inverse sine, so second sine, and then we're going to do 0.3 divided by 2. And when we hit enter, we get 8.6 rounded to the nearest 10th degrees. So that says theta is equal to 8.6 degrees. So that's actually pretty low. That's pretty good in the physical therapy process. It's not always use an inverse sine or a sine. If I had given you the opposite and the adjacent, you'd use a tangent. If I had given you the adjacent and the hypotenuse, you'd use a cosine. Don't use the other three because there are no inverse buttons for the other three. There's only inverse buttons for sine, cosine, and tangent. So again, that was in 5.2 or 5.3. If anyone needs that homework opened back up to achieve those problems now that you've seen it, again, you had to view an example, so you probably already saw this if you're good students. But if you did need a little more practice with just this, let me know and I'll go back and give you another day or two. Email me. If I have 5 people email me, then I'll do it for everyone. But email me today. Don't do this in a week. I'm not going to give you an extension a week later.
All right, so that will be it for today. Like I said, we finished 5.7, so that homework is due in a week. Our test will be a little bit after that, so it'll be the Thursday, Friday combo. And if you are not available to watch hold on, let me start that over. If you only have enough free time to take your test during live class, that 11 to 1 o'clock window, that's okay. Take your test during our class because you have the YouTube replays anyways. So you could take the test during class time and then catch the replay, sometime over the next day or two, or at least before the next class on the following Tuesday, what is that, the 29th, I want to say. That sounds right. So yeah, all right. So like I've said several times already, if you have any questions, please email me. Sorry for the 1 or 2 hiccups today. Again, 'tis the life of working from home with 10 million things going on. I know y'all know how that goes. But yeah, all right. So when we come back next time, we will rock out 5.8. We'll probably get into 6.1 as well, just to go ahead and keep pushing forward. We don't want to fall behind. And then that test will be in a week. All right. Take care, everybody.